I'm currently a postdoc at the Center for Advanced Mathematics for Energy Research Application at LBNL. I'm also a member of the mathematics groups at LBNL. Today, I'm going to present a mathematical algorithm for estimating the rotational diffusion coefficient from X-ray photon correlation spectroscopy data. This work is strongly developed by me, Jeffrey Dunkley, and Jim Zixi. So in this talk, I'm going to answer the following questions. First, what is the rotational diffusion coefficient? Why does it matter? Then, if we want to estimate this coefficient from some experimental techniques, how does one build a mathematical model? Relate the experimental data with the rotational diffusion coefficient. And then on top of this model, the next question is, how does one design a numerical algorithm to extract the rotational diffusion coefficient from the data? And the last question is, naturally, how does one evaluate the performance of the algorithm? Before the rotational diffusion, I would like to talk about the experimental technique I'm going to focus today, X-ray photon correlation spectroscopy, abbreviated XPCS. This technique can explore coherent X-ray beams to measure dynamics of various kinds of samples. Fully coherent X-ray beam can enhance its sensitivity to sample structure and dynamics, enabling XPCS to probe a broad range of length scale and time scale. Here's an illustration of the experiment. In this experiment, samples are illuminated by the beams, and then time series of scattering images will be collected by detectors. These images are actual intensity of the field scattered by the scatterers within the illuminated area. The inhomogeneity of the electron density will lead to the variation of the brightness over the images. Such phenomenon is called speckle pattern. As we observe the sample at different times, the movement of the particles incurs the fluctuation of the electron density. And so the temporal fluctuation of the speckle pattern, which is essentially the variation of the intensity. Inversely, if we analyze the fluctuation of the speckle pattern, we can recover information about the dynamics of the particles. Based on these, XPCS is well suited for studying disordered systems. When applied to such disordered systems, the images exhibit this kind of graining texture. Though visually, it is really hard to distinguish the three images. They are collected at different times. They are actually different. So to analyze the images, correlation functions of the measured intensity are calculated. Our goal here is to estimate the rotational diffusion coefficient from the correlation functions. So what exactly is the rotational diffusion? What exactly is that coefficient? As we saw in the previous slide, the particles would translate and rotate around. A very fundamental process governing these movements is the Brownian motion. Let's say in a dilute suspension on the thermal equilibrium. Due to the random collision from the solvent particles, the trajectory of the particles turn out to be zigzag. Here's an illustration. The blue line indicates trajectories of a few particles. We use a scalar parameter, the translation diffusion coefficient dt, to quantify this process. More specifically, the mean squared displacement is proportional to the translation diffusion coefficient. In addition to the random translation, random collision also results in random reorientation of the particles, which is called rotational diffusion. During this talk, we consider two-dimensional rotation. We could imagine this is on a thin film. The axes that the particles rotate around are parallel to each other. In this case, similarly to translational diffusion coefficient dt, we can use a scalar parameter, the rotational diffusion coefficient dr, which quantifies the mean squared angular displacement. Knowing these two coefficients dt and dr not only provides us insight into the size and mass distribution of the particles, but also the processes they describe play important roles in the dynamics. For example, rotational diffusion is a key factor in the kinetics of macromolecule binding and assembly. My work focuses on extracting dr here. So one way to estimate the translational diffusion coefficient is through the normalized autocorrelation function G2 of XPCS data. Here we use J to denote the images, and the polar coordinate system is used to indicate positions on the images. In this equation, Q is the radial coordinate, and phi is the angular coordinate. T is the lag time between images. The angle bracket indicates the ensemble average. For distance in thermal equilibrium, this ensemble average is equivalent to the time average, so the calculation of this average is taken over the dummy variable tau here. The autocorrelation function correlates points at the same spatial position with a lag time t, then it is divided by the square of the mean intensity here. Here we're considering the system of the free Brownian particles in the absence of external force. This kind of system is isotropic. So in this case, one can derive that this ensemble average does not depend on the angular coordinate phi here. So in practice, to enhance the data quality, the average is also performed over the ring corresponding to the same Q. And we omit the dependence of G2 over the angular coordinate here. Then to evaluate the translation diffusion coefficient dt, we need the following conclusion. For diffusion of dilute monodispersed spherical particles, we have this result G2 QT equals to 1 plus this exponential e to the negative 2 times dt, the translation diffusion coefficient, times q squared times t. So once G2 is evaluated at different q and t, you can feed those evaluated value of G2 to this exponential function and then optimize for the translation diffusion coefficient. And what about the rotational diffusion coefficient? Well, unfortunately, since the autocorrelation function G2 correlates points at the same spatial position, the information in G2 is not sufficient to expose the rotational diffusion coefficient dr. We need something else. Intuitively, like G2 fails to capture the information in pairs of photons correlates on, that is because it correlates points at the same spatial position. So there are actually a large part of information is missing from there. For example, like if two photons are correlated by the rotation dynamics of the particles, but they are scattered along different scattering vectors, then G2 fails to capture all of them. So I will show you actually this information can allow us to estimate the rotational diffusion coefficient dr. So here I'm going to address the second question. How does one build a mathematical model describing the experimental data in terms of the rotational diffusion coefficient? So to expose the rotational diffusion coefficient, here we propose using the angular temporal cross-correlation function. This function is a natural generalization to the autocorrelation function. Here is the definition. In this equation, we still use polar coordinate system to indicate positions on the images. Phi and tau are dummy variables over which the average is taken. In this illustration, we can see that the cross-correlation function can actually correlate 2 points at different spatial positions. While fixing the angle difference delta phi here, the average is taken over these 2 rings. On the right side, I show an example of the cross-correlation function from 40,000 images. In practice, the duration of the experiments is finite, so we can only approximate the ensemble average using finite amount of images. The major difference between the autocorrelation and the cross-correlation is while G2 correlates points at the same position, the cross-correlation is able to correlate points at different spatial positions. Not only different radial coordinates Q and Q prime, but also at different angular coordinates. So if we ignore the denominator, if we ignore the normalization in the autocorrelation function, the number produced by the autocorrelation function G2 is only a subset of the number produced by the cross-correlation function. As Q and T vary, G2 will give us only a data matrix, whereas Q prime delta phi, and T vary, they give us a 4-order data tensor. So the cross-correlation provides absolutely more information. There are a lot more we can do with it. So here we build a mathematical model to interpret the cross-correlation by relating it with the rotational diffusion coefficient dr. So what is the cross-correlation terms dr? Under some mild assumptions in the limit of infinite number of images, we can derive the following results. That the cross-correlation here minus this term equals to the infinite summation on the right-hand side. So in this equation, C is the angular temporal cross-correlation. And these 2 terms are the angular temporal average of the images corresponding to Q and Q prime. And their product is actually the angular average of the cross-correlation. So the left-hand side is the centered cross-correlation data. On the right-hand side, NP is the number of particles in the illuminated area. And this is the term containing the angle difference delta phi. And in this term is related to the static structure of the particles. I2M is the 2M's circular harmonic coefficient of the intensity I. And this intensity I is defined as the Fourier squared magnitude of the Fourier transform of the electron density of an individual particles. So please remember this. Yesterday, sometimes the notation I refers to the intensity of the overall sample, but here I use I to denote the intensity of just an individual particle. And then this is the last term, the exponential decay is resulted from the rotational diffusion. And this is the desired rotational diffusion coefficient, dr. For more details of the derivation of this result, please see this paper. Intuitively, since the cross-correlation correlates different scattering vectors, the interparticle contributes, vanishes. So each particle will contribute to the cross-correlation individually, which explains why the coefficient here is NP instead of the square of it. The exposure of circular harmonic coefficients is from the rotation of the particles. The diffusion leads to the last exponentially decaying term. This term shows that the angular fluctuation gradually decorrelated as the lag time t increases. So as long as we can measure this exponential decay, then we can try to find the rotational diffusion coefficient. So the right-hand side of this equation is the input we need for the estimation of dr. So having this result, how does one design an algorithm estimating the coefficient from the cross-correlation data? Well, to estimate the coefficient dr from the highly complex angular temporal cross-correlation data, we design a numerical algorithm named multi-tiered estimation for correlation spectroscopy, MTECS. To develop this algorithm, we explore the multi-tiered MTIP philosophy of decomposing complex optimization into subparts, which can be solved exactly or efficiently inverted, and then combining the solutions from different subparts in an iteration. More specifically, we first construct a series of operators to break up the cross-correlation into small pieces. Here we assume the cross-correlation function, the center of the cross-correlation function, which is the right-hand side of the previous results. We assume this function is measured at QL, the Q prime in the radial grid, and delta phi in the angular grid, and then for different lag times, for k different lag times. Here we use the lag time starting from t equals to 0 to t equals to k minus 1 delta t, where delta t is the time difference between two consecutive images. Then for each lag time, we have an NQ by n phi data tensor. And then overall, all of these tensors forms the input of our algorithm, a four-way data tensor. So our algorithm estimates the rotational diffusion coefficient dr by breaking up this data tensor into small pieces step by step. So first we separate the parts containing delta phi with the remaining terms. And then from this remaining, we obtain two parts that one is related to the static structure of the particle and another is resulted from the rotational diffusion. And then the last step is to estimate dr from this exponentially decay terms. So first, we break the cross-correlation into this complex unit containing the angle difference. And then the remaining part that contains the circular harmonic coefficient I2M and the exponential decay factor. To do so, we develop the correlation noise projector. So first, we call this equation. Notice that the summation on the right-hand side is from negative infinity to positive infinity. Though this is an infinite sum, since we know that as m increases, the term becomes smaller and smaller, gradually tends to 0. So we can choose a large enough n and then truncate the summation from negative n to positive n with only a bit of difference, with only a tiny bit of difference. Then if we fix L, L prime, and K, just like J vary, this becomes a vector. And then at J and M vary, these terms forms a matrix. Then this term, which contains only n, forms a vector. In other words, using the matrix notation, we turn the summation into the linear system, into a matrix vector multiplication. Here C is the estimated cross correlation, so it is known, and E can be calculated explicitly. It is also known. So the only unknown in this linear system is B. So as long as the number of delta phi, n phi, is larger than 2n, this system is overdetermined, and so it can be solved by a lot of methods such as linear regression. Here we formulate the solver of this linear system as the Tikhonov regularization, which is an L2 norm constrained linear regression. Here is the illustration. So given a current estimation of B, given an initial guess of B, and then the cross correlation projector, the correlation noise projector seeks the minimum perturbation delta B here, such that the perturbed B, which is B plus delta B, can give us the perturbed cross correlation, which is E times B plus delta B here, such that the perturbed cross correlation is within a specific range from the original input C. And the radius of this range is defined by this tau k here, which can be selected based on the quality of the input. So after solving this regularization for all L prime and K, we can get all the vector B together to form a four-way tensor B, which is the input to the next step. So once B is obtained, we can try to get the circular harmonic coefficient I2M and the exponential decay factor. But however, before that, we can try an extra step for further denoising. So here we utilize the following expansion of the circular harmonic coefficient IM. AM are the coefficients of such expansion, and BM and Q are the basis functions. So here JM is the basis functions, UMN is the nth zeros of basis functions of order n. In order to calculate these basis functions, we did a rough estimate of the diameter of the particles. Such estimation doesn't have to be like very precise, as long as it is larger than the actual value. This expansion is valid. And like such kind of estimation can be easily achieved, can be easily obtained in practice. So here, I show some examples of the basis function in these figures. You can see that there's a peak, for example, like this one, this one, this one, and this one. There's a peak for each one of the basis functions. And the number of the basis functions within the measured Q range within the Q grid can be estimated. So based on this number, the expansion can be truncated. I2M can be approximated by the summation of the first few terms. By removing the high frequency terms, we can remove these high frequency noises at a little price. Then leveraging on this finite truncation, the entries of tensor B can be written as this summation. So in matrix notation, fixing M and K, B equals to matrix Vm times Gm times the conjugate transpose of Vm. Here Vm is the matrix of whose entries are the values of the basis function at the grid point, and Gm is unknown here. So in order to solve the values of Gm, we can first calculate the pseudo inverse of Vm, which is Vm dagger here, and then multiply at the left side and right side of Vm dagger to the matrix B, and then we can get the unknown value of matrix Gm. And then for each one of n, we can get a tensor Gm by putting different k together. So this is the input to the next step. So now we're ready to get exponential decay factor from the tensor Gm. In this step, we'll perform the rank 1 tensor decomposition to calculate the coefficient A and N of the expansion and this exponential decay factor. So for each n, the n primes k's entries equals to the product, equals to this product. Notice that the subscript n prime and k here, if we put all the a and n in vector an and all the exponents in another vector, then tensor Gm can be expressed as the outer product of an and its transpose and the vector Rn. So we can apply the rank 1 tensor decomposition to separate all of these vectors. So here, since we assume the first lag time equals to 0, so we'll have constraint R0 m equals to 1, and all the other exponential decaying terms should be between 0 and 1. This could be solved by like a modified alternating least square. Then once we have all of the decays, the last step is to estimate the rotational diffusion coefficient from these exponential decay factors. So for each n, we can get a vector of decay factor. Putting them all together, we have a matrix of such factors. Then by minimizing the square distance between the estimated decaying factor Rkn and the theoretical decaying factor e to the negative 4 times n times m squared times k times dr times the delta t. Then by minimizing such distance, we can give an estimation of the rotation diffusion coefficient dr. So this is the last subpart of the MTECS algorithm. Now we will assemble all the subparts to develop the iterative algorithm MTECS, starting from the initial guess B, usually all 0. And then we can apply the correlation noise projector to obtain an updated B. This is step we input the cross correlation data C. Then through band limiting projector, rank 1 tensor decomposition, exponential fitting, we can get a current estimation of dr. But this is not the end of our algorithm. We can use We can use this current estimation of DR to form a matrix R of the exponential decay factor, and then put this matrix together with the vector AM obtained by tensor decomposition and then put them all together into the outer product to get updated tensor GM, and then multiply VM, the left side and right side of GM, to get updated B. And then we can use B as a starting point of the correlation noise projector in the next iteration. And this could be repeated again and again to enhance the quality of this estimation DR. And we terminate this loop if the difference between the filtered B from two consecutive iterations is smaller than the tolerance. So though DR is the desired coefficient, the terminating condition relying on B makes the algorithm more robust. I would like to emphasize several features of MTECS here. First, in addition to the estimation of DR, we can use this tensor B output by the last iteration to construct the filtered cross-correlation data, which will be much cleaner than the input correlation. This filtered cross-correlation can benefit further analysis. Second, the MTECS algorithm requires almost no prior knowledge, except a rough estimate of the diameter of the particles, which is used by the band limiting projector here. It doesn't have to be super precise estimation, so it can be easily obtained in practice. Third, when additional prior knowledge is available, MTECS can be easily modified to capitalize on such information. For example, if we know the particles are 4-fold or 6-fold symmetry, we can change the correlation noise projector by deleting some terms in this summation, which means then we can do a little bit of modification to the linear system we mentioned before. As the construction of the algorithm, the last question is, how does one numerically evaluate the performance of this algorithm? Well, here we first build a forward solver that simulates Brownian particles in 2D to generate the images we need. Then 3 types of numerical experiments are conducted to test the algorithm. First, for a series of different DR between 0.01 and 0.1, for each one of them, we calculate the cross correlation out of 40,000 synthesized images and then apply the MTECS algorithm to give the estimation. And the second type of experiment, we selected several values of DR and tried algorithm using a smaller number of images to see the behavior of the algorithm. In the third type of the experiments, we add different level of Photon noise to all the simulated images to test the robustness of our algorithm against such noise. So this figure shows the shape of particles we simulated. We'll attach 2 spheres to the end of a cylinder in 3-dimensional space and then integrate along the z-axis to project the dumbbell-like shape into 2 dimensions. Recall that we need an estimate of its diameter. In our experiments, the values we use is 10% larger than the actual value. So on the right-hand side, I show the intensity function I of an individual particle. To make this figure, I take logarithm of the values on the images. Otherwise, we will see only a really bright spot at the center. That's why we have negative numbers shown on the color bar here. The bottom left figure shows part of the simulated samples. The sample is simulated on a Cartesian grid. Totally, we put like 500 particles into the sample. After each time step delta t, we added a bit of Gaussian random number to the position and orientation of the particles to simulate the Brownian motion. Then we use 2-dimensional fast Fourier transform to calculate the scattered field and then synthesize the images. The bottom right figure is an example of the image. Instead of the whole Cartesian grid, we use nearest point interpolation to map the values onto the polar grid shown in this area between the ring at q equals to 50 and q equals to 400. Then the angular temporal cross correlation data tensor was computed using these images, using the values within this area. In the first type of experiment, for several values, for a series of values, DR ranging from 0.01 to 0.1, we collect 40,000 images and then apply the algorithm. This table shows the ground truths, the estimated values, and the relative errors between them. According to the above table, we can see that the algorithms is able to give the rotational diffusion coefficient, it's able to give estimation with all the relative errors more than 3%. And as mentioned before, the algorithms are also capable of filtering the cross-correlation data. In this figure, I show the cross-correlation against the angular coordinate delta phi. Here, the CN dots indicates the data calculated directly from the images, which is the input to our algorithm. And then the black solid line, the black solid curve is the filtered cross-correlation data output by our algorithm at the last iteration. The ground truth calculated from the density of the particle directly is also plotted here as the red dashed curve. We can see that the filtered data is much less noisy than the calculated data. And it almost overlaps with the ground truth. This demonstrates the filtering capability of the algorithm. In the second type of the experiments, for the R equals to 0.01, 0.02, 0.04, and 0.08, we gradually decrease the number of images used from 40,000 to 4,000. Here, for each number of images and each of the DR, we repeated the experiment 10 times, and then, which means we get like 10 estimated values. And then we show that there are stats in this box plot. In this plot, the horizontal bar from the top to the bottom, from here, these horizontal bars indicates the quartiles of the 10 values, from like maximum to the minimum. And the tiny white box is the average of all of these values. And the ground truth is lying beneath all of these boxes. There are some fluctuation of the results due to the random nature of the particles movement. However, we can still see that there's a trend that as the number of images used increases, the results gets better, and our algorithm is able to give reasonable estimation when using less number of images. And in real experiments, the detector can receive only integer number of photons, which introduces some extra noises. This kind of photon counting noises can be modeled by Poisson random variable. In the last experiment, we added a different level of Poisson noise to every images collected. So here DR is fixed to be 0.01, and then the level of Poisson noise is controlled by the factor multiplied to the intensity collected. So since we know smaller the data, more severe it suffers from the Poisson noise. So in the experiment, the data multiplied by 0.25 is the most noisy one. Here I show some examples of the cross correlation data calculated from the images. This is data without the Poisson noise. And then this one is with factor 0.25, which is clearly more noisy than the others. And this one with factor 4.0 actually wasn't suffered much from the additional Poisson noise. Then the estimated rotational diffusion coefficient are shown in this table. All of the relative errors are smaller than 0.0, are smaller than 1%. So demonstrating the robustness of the MTECS algorithm against Poisson noise. At the end of this talk, I would like to mention two of the next steps I'm currently working on. The first is the application of MTECS to the real experiment data. Currently, we're discussing with several beamline scientists to design an experiment. Second, at the beginning of this talk, I assume that rotation is in plane. In this case, a single scalar is enough to quantify the rotational diffusion. For the fully anisotropic rotational diffusion in three-dimensional case, 3x3 rotational diffusion tensor is required. I'm working on adapting the MTECS to a three-dimensional case to estimate the anisotropic rotational diffusion tensor. Here, I would like to thank Jeffrey Duntley and Jim Thaddeus for their contribution to this project as co-author. And I would also like to thank Mark Sutton, Alex Hexamer, and Sujoy Roy for the inspiring conversation. This project is supported by CAMERA, jointly work with ALS and LB on the DOE Office of Science. So thanks for your attention.